Engineering 305, Chapter 2, Problem 19. See it on the screen? The fold-down chair of figure P2-19 weighs 30 pounds and has its center of gravity at G. So I've got the little thing there. Determine the shearing stress on a cross-section of the 3/8 diameter pin at B, which is in single shear. I hope single shear got talked about in class, but either way, it's in the book. We'll start solving this problem. So you can see the picture on the side. We'll wind up relying on that. Lots of geometry we're going to wind up using. Here we go. Engineering 305, problem 2-19. How am I going to start this? I think this is one of the interesting things about this class is, and maybe about all of the engineering classes, I can come in and I can go whip through my solution and you go, wow, he really knows, he knew how to do it. Well, no, it kind of turns out we've done it 3 different times and we picked the one that worked. But what do we know works on this one? And I hope we get a chance during class to show you some of that. In this one, I want to start with a free body diagram for the seat, because that's what we're always going to start with. That point drops a little bit, comes out. This is D, C. Sorry, that's my CG. Are those in line? I have to check those. No, there's a 1 inch difference. So I amplified that, but otherwise that gets lost. And we've seen on other problems how when that gets lost, it creates its own problems. So that's C. That's like that. And then I've got a point A here. And I've actually got one more point back here. We're going to call it, which the book calls E. And we can go back through and put in. I think the picture is important. That's why I'm taking the time to draw it. I think the picture is important because it has good information, like that little 1 inch in there. And then this is 9 inches here. It would probably be easiest if we could just cut and paste and drop that onto our homework set. Do I need anything else? Yeah, I suppose I'm going to put 9 inches from B to E to CE, and then another 12 inches to the top, like that. Now I want to start working on this. If I want to find the internal forces, I think the easiest place to start is finding all the external forces. And so the external forces, really, it's a new diagram. It's a new diagram. It's going to look like this. Like that. And I can say that this distance is 6 inches, that this distance is 1 inch, and that this distance is 21 inches. Hey, remember earlier the other homework problem, I had to turn the light on? Let's do it again here. There you go. There you go. All right. What forces do I have to deal with? Well, that's my weight force. And that's a normal force coming off the wall. And then I have this hanging force, and I'm going to draw it. It's going to be pushing up. And that's A in the Y direction. And I've got some other force. I'm going to draw it. I'm going to draw it this way. I'm going to call that A and the X. Now, here's a little bit of expertise showing up. N is acting this way. I can already see ahead. You know what I want to do? I want to write sum of the forces in the x direction. Well, I've already labeled x and y implicitly because that's my x. So put a coordinate system here. There's y, there's x. Sum of the forces in the x direction are equal to 0, are equal to, and I've got minus n and a plus ax. And there aren't any other things. So I knew, because I know the normal force is going out, it can't be a tension. It doesn't work that way. You can't, it's a homework problem later, but you can't push on a rope. And you can't pull on a gap. It won't work. So I knew that equation was going to set up that way. I know that force is going to be in that direction. So I put it in the right direction to start. That solves really nicely that I have n equals ax. And then my next equation, sum of the forces in the y direction are equal to 0, are equal to a in the y, that's acting up, minus w, that's acting down. That's easy. That's easy. Oh, no. And then lastly, I'm going to get a sum of the moments about, and I'm going to take them about that origin. Why? Because I get rid of ax and ay, and I will have my weight and my normal force together in one. So, and it also highlights that I drew my picture wrong, but that's okay. We'll see the details that I needed later. So that normal force is acting to cause y to rotate to x, so that's a negative from the normal force, and that distance is 21 inches. And w is going to cause it to go the other way. The weight force is going to cause it to go from x to y, so that's a positive. So that's plus w, and I need the distance from here to, and I didn't write that down. No, I go back to the book, go back to the figure. The distance from the CG to that line where A is, you're seeing it's at that 3 inches. So I'll put it on this figure. And write it in there, 3 inches. And now we have that N equals 3W divided by 21. All right. So W equals, from our problem statement, that would be a given up here. Maybe we should have. The weight is equal to 30 pounds, right? N equals 30 over 7 pounds equals 4. How about without a calculator? 4.28 pounds. All right, I got to pull out the calculator. I haven't done it. I haven't gotten the new stuff yet. New calculator yet. Do. Calculator, 30, enter, 7, divided by 4.2857. Okay, so I'm off in the 4th decimal place. Cut me a break. Really? Cut me a break. All right, so that's N equal to 4.28 pounds. W equal to 30 pounds. So now I know AY is equal to 30 pounds from this equation, and I know that AX is equal to 4.28 pounds. All right? Okay. If I have that, what's my next step? Well, let's draw. Now that I have all the external forces acting on the back, except for B, let's see if we can draw a new free body diagram for the back. So that's going to look like this. Points there, and there, and there, kind of. That's A and B and C. And I know the distances. I even wrote them down from before. This is 9 inches, and this is 12 inches. And those are all in vertical alignment, so that's easy. And then the forces that I'm going to have are this. I've got this force of 4.28 pounds. I've got this force of 30 pounds. I've got this force of 4.28 pounds. And I have one more force here, right? That is the tension from B to D. That's the tension from B to D. All right? Okay, time to solve it. How do we want to solve that? How do we want to solve that? Well, I would normally say we should take our moments about A, because that'll get rid of those two forces, and that does more than anything else. However, if I take the moments about C, I also get rid of two forces, because while this acts through A, it also acts through C. So either way, I'm getting rid of a 4.28, whether it's the C or the A, and I'm getting rid of the 30 pounds from the vertical, because they both act through A and through C. So either way, writing a sum of the moments equation really doesn't matter. Let's write this out. Sum of the moments about, well, I think the big thing I really need to know before I do this is, how is this angle defined? How is that angle defined? And so let's take a look at this and see if there's any shortcuts that the geometry provides or dictates that we should use. And I'm going to say, if I look at that triangle, it's 12 inches across the bottom, and it's 9 inches along the top. No, I don't think so. I don't think so. I think that 1 inch, applies to D and G are on a line at that lower level. I'm going to say that, well, that angle is actually 10. This is 10 inches. Because if I draw this out, my CG is here and my point D is there, and that's below that 9-inch level. This is the one more inch. So I think it's a 12-10 triangle, not a, but now that defines this angle. If I know that angle, I am going to break this up into a vertical and a horizontal component, and I'm going to say, yeah, this is going to be, okay, so good. Some of the moments about C, are equal to 0 are equal to, what force do I have? I have this force, which is the 4.28 pounds. I should have looked at the sign. That's going from y to x, so it's a negative. And then that distance is the 21 inches. 21 inches. And then I've got the other force now, which is going to cause this rotation. So that's going to be a plus. That rotation goes from x to y, so that's why it's plus. It's going to be a plus. The magnitude is the tension from B to D. And if I get that tension right, now then that tension, it's this component, which is going to be the cosine of theta. Cosine of theta. No. Hold on. Oh, you know what? I got to get this back too. Sorry, checking my geometry there. This is sine theta. As that angle goes to 90, this would go that way, and then I would want that sine term to go to 1. So that's sine theta, and then times that distance of 9 inches. All right. Now that angle theta is equal to opposite over adjacent. So tangent of theta is equal to 12 tenths, or theta is equal to arctangent of 12 tenths. All right, so now that angle, I got to punch that up on my trusty dusty calculator. 12 tenths, that would be 1.2. That would be a 50.2 degrees. And then I'm going to punch that back into this, but I'm going to reorganize this. Tension from B to D is equal to 4.28 times 21 inch-pounds divided by 9 inches times sine of 50.2. Just for clarity there. Oh, turned off the calculator. Here we go. 4.28 enter 21 times 9 divided by 50.2 sine. And I have 12.9986 pounds. 12.9986. Oh, really? 13 pounds. So now my shear, right? The whole question, the whole point of the exercise, the shear is equal to V over A. Shear stress is equal to the shear divided by the area. 13 pounds is my load. The area, you remember all the way back to the problem statement? We should have maybe put that as a given back on the first page. We'd have to go back to our problem statement. Cross section of a 3/8 inch diameter pin. All right, so given it's a 3/8 diameter pin. Area is pi 0.375 squared. That's the diameter, not pi r squared. That's pi d squared, so I got to divide it by 4. So it's V, the shear, 13 pounds, divided by the area, pi d squared over 4, and that'll get me that answer, which is 117.8, 118 psi. Now, we should put that in context. Big force, small force. Well, am I worried about that pin breaking? Am I worried about, no, that's actually very small. We could actually handle that with a plastic pin, but this is only supporting the weight of the seat. No one is sitting in it. No one is sitting in this at all. So, and if we put someone in that seat, right, they've got the CG 3 inches out. No, no, no. You put someone sitting in that CG is going to move out farther. The CG of the person might be 8 inches away from the seat. It might be farther. If you've got someone like me, like right now, I'm going to slump. Well, that moves that CG farther away from that point C at the back that we're worried about. So that is not a very high load, but we're not talking about supporting any load yet. We're just talking about supporting the seat itself. So there you go. Have a good day.